So now getting into the proof, we suppose that we have a definable set. It is defined by this phi with some free variables expressed by v and w, but there are n of these variables v, and the definable set is a set of tuples of length n. So we're going to prove this by induction, and as usual, we will establish a lemma before getting into the proof. So the two lemmas will in fact be that every term and its associated function, recall seeing terms as defining functions, so every term function is in Dn. That's one lemma, and that empty definable sets are also in Dn will be the next lemma. Now that's almost the whole proof. An empty definable set is a set for which there are none of these variables expressed by w, right? So the length of this is 0, so to speak. Whenever you have a set defined by a formula like that, we call the set empty definable. And in general, whatever set you have to draw from to fill in here in order to define a set, we put that collection here. In any case, that concept may sort of sink in more just from practice and use of it. So we'll start with the first lemma, that every term function is a, the graph of the term function really is in Dn, or Dn plus 1 if we, think of the argument as being a tuple of length n and the graph being of length n plus 1. So in any case, more precisely, if we have some term of n free variables, then the graph of it being n plus 1, an n plus 1 tuple defined in this way, and the meaning of this is defined as in earlier videos, the graph of this term function is in Dn plus 1. We proved the lemma by induction on the complexity of terms. If t is a constant, then we want to show that the denotation of the constant is in d1, right? Because it's a 0. The arguments have length 0, so 0 plus 1, that's d1. So having set things up, up to this point, I'll sort of end here and really get into the rest of the proof in the next video.